Hello everyone. Let's discuss about the stereochemistry of radical reactions. When radical halogenation produces a chiral center or takes place at a hydrogen on a chiral center, the product is a racemic mixture of 50% R and 50% S enantiomers. For example, a reaction between butane and bromine is shown here. The product is 2-bromobutane. In the product, the carbon number 2 is a chiral center. So although the product has a chiral center, but because it's a 50% R and 50% S, the product is optically inactive because racemic mixtures do not interact with the plane polarized light. Another principle you will see here is, which we learned earlier too, that if the reactants are achiral, as in our case here, the product will always be optically inactive. We learned earlier that optically active products are only obtained when the reactants are either optically active or the environment in which a reaction is taking place is optically active. None of the reactants or the environment are optically active, hence the product is optically inactive. For simple alkyl radicals, the carbon which bears the radical is a sp2 hybridized. For example, this carbon is sp2 hybridized, and we know that sp2 hybridization has a trigonal planar structure where the three bonding uh, units or bonds are in the same plane, and it has a unhybridized p orbital, and that unhybridized p orbital is above and below the plane. The unpaired electron or the radical resides in this p orbital. This carbon is sp2 hybridized, and it forms bonds with other atoms such as hydrogen or maybe another carbon on these three bonding sites, and the unhybridized p orbital holds the radical electron. So as we learn in the radical reaction mechanism, in the propagation step, the alkyl radicals form a bond with the halogen to create the alkyl halide, as shown here. Now we know that the uh, radical intermediate has a sp3 hybridized state, and the bonds are in one plane as shown here, and the unhybridized p orbital holds the radical electron. Now bromine can attack or can make a bond from the bottom, or it can make a bond from the top. So in 50%, and both possibilities are equally likely. So 50% of the time bromine will form a bond through the bottom attack, so resulting product will be R2-bromo butane, and the remaining 50% the bromine will attack from the top, and the resulting product will be S2-bromo butane. So that's why in radical halogenation the end product is a mixture of R and S enantiomers. It's a racemic mixture. Allelic halogenation is one of the most common and versatile radical reaction. Allelic group is a propenyl group such as this group is known as allelic group or allyl group. In chapter number 6, we learned that propene, just like any other alkene, undergoes addition reaction at room temperature. And if that addition reaction is with a halogen, then we call this reaction as halogenation reaction. For example, propene reacts with bromine at room temperature to give us 1,2-dibromopropane. And this reaction is a anti-addition reaction where the bromo groups are present opposite to each other. And this reaction is a simple addition reaction, and we learned about this reaction in chapter number 6. However, if propene is allowed to react at elevated temperatures, such as 350 degrees Celsius, high temperature, uh, then instead of undergoing 1,2 addition reaction, the reaction will take place at allelic carbon. Now, what is allelic carbon? The carbon atom which is adjacent to the carbon-carbon double bond is known as allelic carbon. So in the allelic group shown here, the allelic carbon is this one. So it's the carbon atom which is next to the carbon-carbon double bond. So therefore, if halogenation is carried out at elevated temperatures such as 350 degrees, then instead of undergoing addition at the pi bond, the reaction will take place at allelic carbon, as we can see here. So the product will be 3-chloropropene. This reaction is known as allelic halogenation. So if we want to carry out halogenation at the carbon atom next to carbon-carbon double bond in propene, then we carried out the reaction at elevated temperatures. However, if we want to conduct an addition reaction, then the reaction is carried out at room temperature. In order to understand why halogenation takes place at allelic carbon, we need to take a look at the bond dissociation enthalpy values of various carbon-hydrogen bonds in propene. As we can see that the CH bond which are connected to the carbon-carbon double bond has higher bond enthalpy value or bond dissociation values as compared to the carbon-hydrogen bond at allelic position. There is a difference of about 92 kilojoules, almost 100 kilojoule difference. So it means the allelic CH bond is more easy to be broken up. So why it's so? The reason is after the allelic carbon hydrogen bond breaks, it generates a allelic radical. Allelic radical is resonance stabilized, so it has a resonance structure, and because of the resonance stabilized structure, allelic radical is exceptionally stable. So this is stable. In fact, allelic radical is even more stable than tertiary radical. So breaking an allelic CH bond generates a resonance stabilized radical, and this is even more stable than tertiary radical. So one thing is clear now, that if a radical has to be formed, then the alkenes prefer to form a allelic free radical other than rather than a radical at any other position, because allelic radicals are more stable. So reacting propene with either bromine or chlorine at elevated temperature illustrates a very important point about organic reactions. The point is that it is often possible to change the reaction mechanism by changing the conditions. For example, if propene reacts with bromine at room temperature, then the product will be a simple addition reaction. In simple addition reaction, we have a dibromo product. However, if we carry the same reaction at elevated temperature, then the reaction will give us a mono halogenated product at allelic position. The reason is that at elevated temperature, uh, there is enough energy available to break the carbon hydrogen bonds, and when these homolysis of this carbon hydrogen bond happens, it generates radicals. So in other words, at elevated temperature, more radicals are available. So if more radicals are available, of course they will form the more stable radical, and we know that the allelic radical is more stable, and hence allelic radical is formed, which results in formation of this allelic substituted product. However, at room temperature, not enough energy is available. At room temperature, the kinetic energy is not high enough, so these carbon hydrogen bonds are not likely to break, but the pi bond is more likely to break because it doesn't need that much energy. So hence the reaction will be a addition reaction. So by changing the conditions, we can alter the outcome of the reaction. It is also possible to carry out the allelic bromination at lower temperatures also. In previous slide, we learned that allelic halogenation takes place when the reaction temperature is extremely high, such as 350 degrees Celsius. However, it is possible to conduct allelic bromination at moderately low temperature, just above room temperature, with the help of a reagent called NBS. NBS stands for N-bromosuccinimide, and this is the structure of N-bromosuccinimide. This reaction is catalyzed by sunlight or light source, so that's why H nu stands for it. The reaction takes place in presence of light, and dichloromethane is used as a solvent. So N-bromosuccinimide in presence of dichloromethane and light results in allelic bromination of alkenes. So in this case, the carbon atom next to the double bond is a allelic carbon. So therefore, this position is allelic as well as this position is also allelic. Both are equivalent. So either one of that position will get attacked, and we will get a bromo substitution at allelic position. Allelic bromination takes place via radical chain mechanism. It is similar to the mechanism which we learn in case of halogenation of alkanes, and this mechanism also involves three steps. The first step is chain initiation step. The chain initiation step involves the formation of bromide radical and succinimide radical from the NBS by homolytic cleavage of N and Br bond. So this bond breaks homolytically. Homolytic cleavage means one electron will move to the bromide one side, the other one move to the nitrogen. and this homolytic cleavage will produce these two radicals. The next step is the chain propagation step. The bromide radical, which was formed in the chain initiation, reacts with the alkene, and it results in formation of an alkynyl radical, as shown here. It's allyl radical, and we know that allyl radical is stable because of resonance, and the allyl radical then continues the propagation of various steps, and by grabbing a bromide group and resulting in formation of a bromo substituted alkene, and this substitution takes place at allelic position, and along with the bromo substituted product we will generate another bromide radical. This bromide radical will undergo the same propagation step one more time, and then the resulting product will form another bromo radical, and that bromo radical will undergo same propagation step, and it will result in another, and this process will continue until we run out of all the alkene molecules. So that's why it's called a chain propagation. It's like a chain, it continues. The third step of this mechanism is the chain termination. In this step, destruction of radicals take place. The destruction of radical can take place in three different ways. The one way is that two bromo radicals find each other, they collide with each other to form a bromine gas. The other possible way is that allyl radical combines with the bromide radical to give us the allelic bromide, and then finally the third possibility is that the two allyl radicals combine to form a longer alkene. Now we must understand that chain termination is rare as compared to chain propagation. The reason is, in the beginning we have lot more alkene molecules, so the chances of two radicals to find each other and then collide are very rare. So chain termination only happens when all the alkene molecules are already reacted, so chain propagation has already exhausted the supply of reactant material, and now we are left with only radicals. Then chain termination step takes place. So chain termination usually happens at the end of the reaction. In step 2 of propagation step, we saw that the allyl radical reacted with the bromine gas. So that bromine gas, which is necessary for chain propagation, is formed by the reaction of NBS with HBr as shown here. Now this mechanism poses one important question. That question is that when in the beginning we do produce Br gas or bromine gas, and also we have propene or alkene in the beginning of this reaction. Now the question is, why does this reaction proceed to give us a allelic product, and why not it undergoes the simple addition and give us just the addition product? Because we have bromine gas and we have alkene, why this reaction does not take place? Okay. The answer is that the rate of chain propagation steps are much more faster than the rate of this electrophilic addition of bromine to alkene. So furthermore, the concentration of bromine is very low throughout the course of the reaction, so that also slows down the electrophilic addition reaction. So therefore, because of the faster rate of reaction of allelic addition, allelic substitution is responsible for the allelic product. And also we don't produce enough Br gas or bromine gas to undergo the electrophilic addition reaction. So that's why under NBS and light, the alkenes give us allelic substitution and not the electrophilic addition reaction. Let's take a look at this problem. In this problem, one octene is undergoing halogenation reaction with N-bromosuccinimide in presence of methylene chloride. We know that in this case, the N-bromosuccinimide favors the bromination of allelic carbon, and in one octene, the allelic position is carbon number 3. So therefore, we would expect this to be our product. However, we found experimentally that along with the 3-bromo-1-octene, which was the expected product, we also synthesize 1-bromo-2-octene. Not only that, 1-bromo-2-octene indeed is our major product. So how do we explain that? Now, the explanation of this problem comes from the fact that before the bromination step, this reaction generates a alkene radical, and that alkene radical is a radical where the allelic position has a radical electron. So therefore, in this reaction, during the propagation step, this radical will form, and that's the radical is at allelic position. Now we know that allelic position radical has a resonance stabilized structure, so it will show this resonance, and we will get another structure in which the double bond is between carbon number 2 and 3, and now the radical is at position number 1. So now both of these resonance structures can undergo substitution with bromine, and in case with this we will get product at bromo at number 3 position, and the further substitution reaction at the second resonance structure will give us a product where the bromo group is at number 1 position. Now, why the 1-bromo is the major product? The answer comes from the fact that in the number 1 position, the double bond is more substituted, and we know that the more substituted double bond is more stable. So hence this 1-bromo product is major product because it ends up giving us a more substituted, more stable alkene. Radical autooxidation is one of the most common destructive reaction for materials such as food. This kind of reaction is known as auto-oxidation reaction because this oxidation process requires only oxygen and nothing else. No other oxidizing agent is required, so that's why it's known as auto-oxidation. This reaction also takes place by a radical chain mechanism, which is very similar to that for allelic bromination. If you open a bottle of cooking oil which was left closed for many days or maybe many weeks, when you open it, you will notice a small hiss. air. Uh, that hissing sound is because of the fact that the auto-oxidation has consumed the oxygen from inside the bottle, which created vacuum. So when you open it, the outside air rushes in, so that's why you hear the hissing sound. Uh, in auto-oxidation, it kind of destroys food such as cooking oil, so it's not a good process. Um in this section, we will concentrate on auto-oxidation of hydrocarbon chains of polyunsaturated triglycerides, such as found in cooking oil. The characteristic feature of the fatty acid chains in polyunsaturated triglyceride is the presence of 1,4-diene. So that means that we have long hydrocarbon chains in cooking oil, and there are certain positions where we have a 1,4-diene. So two double bonds are separated by 4 carbons. So the carbon atom in the middle of that 1,4-diene is doubly allelic position. Double allelic position means that this carbon is allelic to this side as well as allelic to the other double bond. So that's why it's called a double allelic hydrogen. So this double allelic hydrogen or the double allelic position is particularly reactive towards radical reaction because a double allelic radical is extremely stable. So if a radical forms there, it's extremely stable because it has double resonance structures. Because this radical is extremely stable, so hence if we have a hydrogen at this position, that hydrogen is easily removable and it will generate a radical here. So that's why double allelic position is extremely reactive position towards radical reactions. The auto-oxidation of unsaturated fatty acid chains begins when a radical initiator abstracted doubly allelic hydrogen as shown here. The initiator can be formed either by light activation of an impurity in the oil, or it can be formed by the thermal decomposition of peroxide impurities. Whichever way this initiator is formed, whenever it's formed, it will initiate the uh, radical auto-oxidation of 1,4-diene functional group in the unsaturated fatty acid chain. In oils, usually they contain fatty acid chains anywhere from 14 to 18 carbon long, and 1,4-diene does not mean that the double bonds are at position number 1 and position number 4. In this context, 1,4 means that they are anywhere in the middle of the chain, but they are starts at, if one starts at number 1, and then the second double bond will be at number 4. So in other words, the bonds are separated by 4 carbons. That's what it means. So because of that, the middle carbon, as I explained in our previous slide, so this carbon is doubly allelic position. So the radical initiator, whenever it's formed from the impurity by the action of light or thermal decomposition, it will uh, cleave one of the allelic position hydrogen homolytically, and it will generate a uh, radical at doubly allelic position. Now this radical is extremely stable because it has twice the resonance contributing structure as the normal allelic radical. So therefore this doubly allelic radical is quite stable. The doubly allelic radical, which is formed by the action of radical initiator, is then further reacts with oxygen. Now oxygen itself present as a diradical. Now diradical oxygen is a molecule in which each of the oxygen atom has one radical. So normally this diradical is not very reactive. So it's actually quite unreactive. But when this oxygen diradical comes in contact with the allelic radical, as shown here, they combine to form a peroxy radical. Now this peroxy radical is quite reactive, and this peroxy radical will react with another molecule of fatty acid chain, the doubly position in the middle of 1,4-diene group, to give rise a new radical, and that new radical, alkyl radical, will react with oxygen one more time. So it will react with another oxygen reaction will generate another peroxy radical. Another peroxy radical will combine with another fatty acid chain, and another fatty acid chain will then generate another doubly allelic stable uh, radical, and that will react with another oxygen. You see where I'm going right now. So that means is that this reaction will become a chain reaction. So once it starts, it's going to continue to break down all the fatty acid molecules present in the oil. Now when that happens, eventually all fatty acid chains which contain doubly allelic position will undergo this radical autooxidation, and they will form eventually a hydroperoxide as shown here. Now the ultimate fate of this hydroperoxide once it generated is a little bit more complex. Hydroperoxide itself is not extremely stable molecule, so it will undergo further degradations. In one of that degradation process is that this hydroperoxide will degrade into a short chain aldehyde or ketone. These short chain aldehyde and ketones are foul smelling compounds, and they are responsible for that rancid smells which is familiar to anyone who has smelled old cooking oil or any old fatty acid or fatty substance, uh, and that foul smell indicates that the oil has undergone many steps of autooxidation, and most of the um, unsaturated fatty acids have been degraded into these peroxides, and then peroxides have been converted into aldehyde and ketones. Some studies have suggested that products of autooxidation are maybe they are or they may be carcinogenic, and they may also be toxic. So we should avoid using old cooking oil, especially the one which smells pretty bad. In order to prevent the radical autooxidation process, we can do a couple of things. So first thing is we should prevent uh, the fatty acids or the oils from contacting with direct sunlight or light, because the action of light generates the initial radical which starts this whole process. So we should store the oil in dark place, or preferably in cold temperature also, because thermal decomposition may also lead to the to formation of the initial radical. The second method is that we should add a radical scavenger such as vitamin E. So vitamin E is a naturally occurring antioxidant. It reacts with the initial peroxy radical. So this peroxy radical, when it's formed, uh, vitamin E will react with this peroxy radical and it will generate a product which is known as phenoxy radical. This phenoxy radical is stable. So vitamin E will capture the peroxy radical and it will prevent it to undergo the chain reaction. So it will stop that peroxy radical from decaying any more fatty acid chains. The reaction of vitamin E to the initial peroxy radical is shown here. The initial peroxy radical will react with the vitamin E and it will generate a phenoxy radical as shown here. Now phenoxy radical is resonance stabilized and this phenoxy radical will capture another molecule of peroxy radical to generate a peroxide group. So this peroxide derived from vitamin E is relatively stable and it does not undergo any more chain reaction or it does not undergo any harmful degradation. So that's how vitamin E prevents the autooxidation of fatty acid chains. In chapter number 6, we learn about the addition of HBr to alkenes, and we also learned that it gives Markovnikov's addition, in which the Br goes to the carbon where we have less number of hydrogens, and hydrogen goes to the carbon where we have more number of hydrogen. So the product in this case will be 2-bromo 2-methyl propane. So this is the normal Markovnikov's addition. So when in early 1900s chemists were investigating this reaction, they were observing that whenever they conduct the addition reaction of HBr to alkene, sometimes they would get the Markovnikov's addition and sometimes they would get the non-Markovnikov's addition. So that puzzled them quite a bit, that why in some cases they are getting a Markovnikov's product and in why some in other cases they are not. Eventually in 1930s it was found that if the HBr addition reaction is carried out in absence of peroxides, then the normal Markovnikov's addition reaction takes place. However, even if a small trace of any peroxide is present, then the product will be a non-Markovnikov's product. Okay. So now this reaction has given us a utility to produce any desired addition products. For example, if we want to produce a more substituted halogen addition product, then we will conduct the HBr addition in absence of peroxide, and that reaction will give us a normal Markovnikov's addition. However, if we want to produce a product in which the halogen or the bromo substituent is present at the at the less substituted position, then we will conduct the same reaction in presence of peroxide. That reaction will give us a non-Markovnikov's addition. So quite useful reaction. So therefore we can say that a radical addition reaction of HBr to alkene gives us a non-Markovnikov's addition product. Radical addition means the reaction which undergoes addition in presence of peroxides. It should be noted that the radical addition only takes place with HBr. HCl and HI do not undergo the radical addition reaction, or in other words, the non-Markovnikov's addition of HCl and HI in presence of peroxide is not possible. So HCl and HI give only the Markovnikov's product. The mechanism of this reaction undergoes by the same radical chain reaction mechanism. The first step in this case is also the chain initiation step, and the peroxide is the one which initiates the reaction. Most common peroxide which we use is a dialkyl peroxide, such as a dimethyl peroxide or any other alkyl peroxide. In the chain initiation step, the dialkyl peroxide homolytically cleave to produce two alkoxy radicals. These alkoxy radicals will combine with the HBr to produce a bromine radical. This bromine radical will participate in the chain propagation step, and it will give us the halogenated product. In the chain propagation step, the bromine radical which was produced in the chain initiation step combines with the alkene, and the product is a tertiary radical, and tertiary radical can only be formed when the bromine is uh, uh, is uh, um, present at the carbon atom which is less substituted. So that's the non-Markovnikov's position. So we know that tertiary radical is more stable, so this reaction is favored. And the chain propagation continues when the alkyl tertiary radical combines with another molecule of HBr to produce the desired product, and this step will also generate a new bromide radical. This bromide radical will react with another molecule of alkene, and we will form another product plus another new bromide radical, and hence this process continues. It's a chain reaction. And finally, in the chain termination step, the two bromide radicals combine with each other to give us a bromine gas. So this step involves the destruction of free radicals, and the another way to destroy the free radical is the combination of bromide radical with the alkyl radical to give us a dibromo product. This pair of reactions illustrate how the product of reaction can be changed by a change in experimental conditions. If we use polar addition of HBr, which is the HBr acid in presence of water, then the resulting product will be a Markovnikov's addition product, in which the bromide will be added to the more substituted carbon. However, if the same reaction is carried out in presence of a radical or a peroxide, then Br addition will take place at less substituted carbon. So we can alter the outcome of a reaction by changing the condition of the reaction. With that, we conclude chapter number 8. So in this chapter, we learned about haloalkanes. We learned how to produce haloalkanes with the help of halogenation reaction. We also learned about the allelic halogenation and auto-oxidation of alkenes. And finally, we learned about the radical addition of HBr to alkenes. This radical addition of HBr to alkene gives us a non-Markovnikov's addition product. Thank you for watching the video. If you have any question, please let me know. Have a wonderful rest of the day. Bye-bye.